All right, on my watch, it's 3 minutes past 3, at least our time zone. So I would suggest that we begin with this presentation. So everyone, I bid you a very warm welcome to today's webinar with the title Simulation of Hydraulic Losses of a Single-Speed Transmission in an Electric Drive Unit using Particleworks. My name is Alina Dübler from the company EngineSoft, and I will be your host today. Before we begin, I would like to say a few short words about organizational details up front. So bear with me for just a moment, please. In order to guarantee a presentation without any interruptions, we have turned your microphones on mute, and I kindly ask you to keep this setting for the course of the webinar, as interruptions will make it hard to keep track of the contents we are going to present. If you have any questions coming up, please feel free to use the panel or the chat to communicate us your questions in writing. At the end of the webinar, we will make time for a Q&A session where we will answer as many questions as the time allows. What I also recommend to you for optimal audio quality is the use of a headset. Our experience has also shown us that a poor internet connection will have a negative effect on the audio quality, so we recommend that you make sure your connection is reliable. This being said, let us have a look at the agenda for today's webinar. Today, we have five short presentations planned for you by two different speakers, whom I will introduce to you in a second. This session's focus lies on the fourth and fifth presentation that you can see on the agenda, and it should take roughly about 50 minutes, just depending on how much time we will spend on the Q&A session in the end. I will just give you a moment to read through the agenda before moving on to the introduction of the speakers. All right, I think this should do. First, I would like to introduce our guest speaker, Tobias Moll from the Institute for Combustion Engines at RWTH Aachen University, where he currently works as a research associate. From him, you can expect two presentations today. Mr. Moll, thank you for being here. The other speaker I would like to introduce to you is our very own Simon Habecke, who works as application engineer here at EngineSoft Germany. He has prepared 3 introductory presentations on Particleworks and its moving particle simulation for you. Welcome, Simon. We're glad to have you too. All right, I'm not going to take up any more of your time, and I would now like to pass on the moderation rights to Mr. Simon Habecke, so the first presentation of the webinar can begin. Let me just, here we go.
Yes, okay, you should be able to see my screen now. So thank you, Alina, for the warm welcome, and also warm welcome from my side. I will take you through a brief technical introduction about the moving particle simulation. Then afterwards, how the simulation process in Particleworks is designed. So Particleworks is a commercial tool using the moving particle simulation. And then finally, before passing the word to Tobias Moll, I will give you an overview about some reference applications from the powertrain, or broader speaking, from the drivetrain sector, based on customer references that have been presented on other conferences before. So jumping into the first topic. So the moving particle simulation was originally proposed in 1996 by Professor Koshizuka. Professor Koshizuka, he's a professor at the Graduate School of Engineering at the University of Tokyo, and also a co-founder of Promotech Software. So what is the MPS? Basically speaking, in one sentence, the MPS is a deterministic Lagrangian method to simulate liquids. But what does that specifically mean? So starting from classical methods, CFD methods, such as the finite volume method, in there the fluid is normally discretized on a numerical grid, where basically mass and momentum is exchanged between the different cells, and this concept is called a Eulerian approach. And then on the other hand, the basic idea of the moving particle simulation, instead of passing the mass and the momentum between the cells, the general idea is to discretize our fluid, our liquid, by a set of particles that interact with each other and also move. So we can basically see them as dynamic calculation points that do not exchange mass, and this on the numerical side already makes life much easier. And the MPS also approximates the Navier-Stokes equations. So how to describe Particleworks, which is a commercially available tool by Promethex software that uses the moving particle simulation. So Particleworks is a CFD software based on the MPS, and it solves the Navier-Stokes equations in incompressible condition. So that means that it's mainly applicable to liquid flow simulation, and it's commonly used to simulate free surface flows, but also liquid jets. But it can also simulate granular material like powder and also rigid floating objects. And these two examples we see here are the oil splashing in a transmission, and also on the right-hand side, a bearing with grease, which means that in principle we can also simulate highly viscous, or in that case actually quasi-solid materials. So how does the general simulation process in Particleworks look like? It starts that we export our geometry data from CAD. In here, it's fine enough to just roughly group the different bodies based on the kinematic conditions that we want to implement later on in our simulation model. So for this two-speed reduction gearbox, we'd import the housing, the input shaft, the output shaft, and then one file per other rotating component, which in that case would be the different gears. Then after importing the model, we'd define the analysis conditions. So this starts with defining our material properties, specifically speaking, in that case, the oil properties being characterized by the density, viscosity, the surface tension, and all these kind of parameters that characterize our liquid. Then in the next step, we can set the kinematics, predefine the kinematics of our system. So for the application of a gearbox, that would mean that we define the rotational velocities of the different shafts and gears. And then in that step, last but not least, to introduce our liquid particles into the simulation, we could either use inflows and outflows, or if we have a pre-filled sump, for example, we can also use this sort of filling plane, which will pre-fill the sump based on the filling height or a predefined volume, and then also, of course, set some numerical parameters for the solver. Then transitioning to the pre-processing, this is a fully automated process in Particleworks, which in the end translates the geometry into the internal calculation model that the solver will actually use, but also produce our initial particle placement. So before running the actual simulation, we will already see the amount of fluid being filled into our system. Then during the actual calculation, we can leverage NVIDIA-based CUDA GPUs. So there is a GPU-based solver available, which makes a lot of sense for particle-based methods in general. but we can also leverage existing CPU clusters. And from the software point of view, both the user interface as well as the solver run on Windows and on Linux. And then transitioning to the last step, the post-processing. In there, of course, we can visualize the oil flow, we can export animations, as we will later see, evaluate the churning losses, but also perform virtual measurements, so to evaluate flow rates and also the oil distribution for different parts of our system. So cut down, what's the advantage of the simulation process, since meshing is being taken out of the equation in comparison to mesh-based CFD. This saves us a lot of time. Then the state-of-the-art GPU-based solver gives us a huge advantage. And in terms of simulation process robustness, it's also very easy to implement complex kinematics. So now, before transitioning to BioSmall, I will give you a few application examples, as said, based on customer references that have been presented on conferences before, all ranging from the powertrain or drivetrain sector, since the borders are more and more being removed in these traditionally separated sectors. So the first application I'd like to focus on is piston cooling. In here at the last CAE conference, we had a very nice presentation from Ducati Cars. So the recording of that presentation is still available on the homepage of the CAE conference. And in there, Ducati presented their use case on how Particleworks helped them to evaluate and also optimize the effect of different nozzle designs for the spray pattern on the undercrown of the piston, and also evaluate and then therefore optimize the HTC distribution on the undercrown of the piston. Then another case study, which was presented in collaboration between EngineSoft and Ricardo, focused on the thermal effects of an electric motor. In there, the overall target of the application was to compare the results of simulations with experimental measurements, so with temperature measurements from the test bench, with simulated temperatures from an FE model. And in there, Particleworks was used to simulate the windage, so the airflow inside of the e-motor, but then also the oil distribution and also the HTC distribution on the windings, which were then used in a later stage to calculate the temperature distribution in the windings. And finally, the temperatures were compared between the resulting temperatures from the simulations and from the measurements. In there, the overall requirement was to lay within a deviation of less than 5 degrees Celsius. And lastly, this criterion could be met with a difference of less than 3 degrees Celsius. And also here, the original talk is still available at the homepage of the CAE conference. Now, shifting a little bit more into the gearbox or transmission sector. It's one of the sectors where Particleworks is very broadly being used by major players. This case study that I'd like to briefly talk you through was presented at the CAE conference 2016 by Comer Industries. In here, we have a 2-speed reduction gearbox from a harvester machine, and the initial question was whether it is possible to have the model and the simulation done in roughly 3 days, which could be done in the end. And in here, initially, the oil flow was validated based on these characteristic patterns that could be identified at the top of the housing. And then Particleworks was used to evaluate the lubrication, which was led by these internal channels to the bearings. And finally, this project could help to investigate the effect of the initial oil level onto the lubrication. Then another very interesting application from Uland was regarding the positioning of the scavenge part. So in here, we could also simulate the circulation of oil inside of a transmission and also see the behavior, the sloshing behavior in the transmission due to dynamic driving conditions, and therefore also validate that the pump intake is always well fed with oil. So that would be the last slide from my presentation. I'll be happy to pass over to Mr. Moll.
Yeah, welcome from my side to this webinar. And now I want to show you some application of the software Particleworks. So the simulation of the hydraulic losses of a single-speed transmission in an electric drive unit.
We cannot hear you anymore. Your audio is off.
Oh, sorry.
There you go. Now you're back.
Okay, yes. Sorry. Welcome from my side. I was muted, unfortunately. Now I would like to show some application of the software Particleworks. And first of all, I would like to begin with a brief introduction of the Institute for Combustion Engines at RWTH Aachen University, where I work. So the structure of the institute, we have one director, that is Professor Stefan Kischinger. We have a junior professor, Professor Jakob Andert. He is Professor for Mechatronic Systems for ICE. We have 3 chief engineers and overall a bit more than 300 employees, which distribute almost equally to scientific employees, non-scientific employees, and student workers. So here you can see the distribution of the research associates according to the different research fields. So you see still in the traditional areas, gasoline engines and diesel engines, there are many research associates, but at the moment already most of the colleagues are working on electrification, electronics, and software. There are also colleagues in operations and the field of overall vehicle design. And there's one colleague that's actually me in the transmission area. There's a short overview about the research supports. You see VKA research into all directions for future mobility. So we go for battery electric vehicles and plug-in hybrids, but also do research on fuel cells and combustion engines, which use hydrogen. And we also develop synthetic fuels, which could be used to go on with the traditional internal combustion engines. So that was the introduction to the Institute, and now I want to give the background and the overview of the internal research project for transmission losses. So the research project, which is actually my PhD work, this is about a co-simulation of efficiency, lubrication, and heat management for transmissions with integrated electric machine. So this is an exemplary setup of a co-simulation, this case for a hybridized dual clutch transmission. So the idea is to have one model. In this case, I use a GT Suite, where I have a thermal network of the transmission and also one longitudinal dynamics model included. And I have one model for the simulation of the transmission losses. This I do in MATLAB Simulink. And you see here on the left side, we have, in this transmission, we have an oil sump. So oil goes, you see in yellow, orange here, the oil volume flow. We have an oil sump and an oil pump, oil cooler. And with this oil pump, oil is pumped to an electric machine, which is integrated to cool the electric machine. And from there, we have a split. Some oil goes into a reservoir, which is a buffer to store oil and to distribute it to different parts of the transmission. And other part goes to the transmission gear set directly and back to the oil sump. And so we have heat transfer from the electric machine, between electric machine and the oil circuit. And we have, of course, a heat transfer between the transmission and the oil. So the losses generate heat. And we have heat transfer between the transmission and the environment. So an idea is now that for every time step, we get from the GT Suite model the torque, the speed, the oil temperature, the current oil temperature, and the current oil volume. So this is used in the MATLAB Simulink model. There, the losses are simulated, and the power loss is transferred back to the GT Suite model, where this acts as a heat input. So, and for another time step, this leads, of course, to a change of oil temperature. Also, the oil volume in the sump, which is relevant for the drag losses, may change. And so, after next time step, all these values are transferred back to the Simulink model, and this continues until the simulation stops. So this is the idea of the co-simulation. And of course, it is important. And of course, it's important to simulate the losses as accurate as possible. And because of that, we did an internal project to validate the MATLAB Simulink model. And for this, this internal research project was done together, or was done at FEV Europe GmbH. The Institute for Combustion Engines has a research cooperation with FEV. And for this tests, for this research project, we used this transmission, which you can see here on the left. So this is one-stage single-speed transmission. Quite simple, but perfect for such kind of validation. So we have one input gear here at the bottom and one output gear at the top. Number of T's is 50 for the input, 43 for the output. So we go a little bit into the fast. We have a passive lubrication by an oil sump, and we have an optional active lubrication with an oil pump. So you can see here at the bottom there's an adapter for the oil pump. So here's the connection to an oil pump. At the test, it was external, but it could also be directly flanged to the transmission. Then we have an oil guide here at the left inside the housing with 4 orifices, 2 you can see in the middle. It's behind the gear mesh, and 2 orifices at the top for the lubrication of the upper bearings. The direction of rotation is can be seen here. So the input gear in this view is counterclockwise. The active tool switch 43 millimeters, so quite wide gears. center distance of 145 millimeters. And this kind of transmission could be used in a range extender vehicle, in a range extender unit of a battery electric vehicle. And of course, similar transmissions are also used directly for battery electric vehicles between e-machine and wheel, but there, of course, with a larger gear ratio or even more than one stage. So in this research project, we had 2 test setups for the investigation of transmission losses. On the left side, you see the test setup for the drag torque measurements. So here you have the transmission installed. Output is running free, and at the input, here we have an e-machine and a measurement of the torque. You can also see here the oil pump and the cooler, because we did these tests with a constant oil temperature of 40 degrees. Here, and you can see this a little bit larger. And for this test, we had one transparent half of the housing, which was very nice. So we could really see the flow. And here on the right side, you see the other test setup that was for the measurements of losses under load. So with the full aluminum housing, and then of course 2 e-machines, one at the input, one at the output. And they also we measured the torques and could calculate efficiencies. Now here you see a little bit larger. So we investigated 3 different oil levels for this drag torque measurements. So the low oil level, where just one tooth head is dipped into the oil. Then we have a medium oil level, which you can see here. So the bearing is just dipped into the oil, and the higher oil level, where we go up to the axis of the lower gear. And furthermore, we investigated 3 different oils, 3 different viscosities. But I will come to that later. So then, I did the simulation in parallel to the tests. I did the simulation of hydraulic losses with Particleworks. Here on the left, you see the geometry and the definition of the oil fill level. The geometry comes directly from CATIA V5. So I have basically 3 main parts: everything belonging to the housing, and then everything belonging to input shaft, and everything belonging to output shaft. The bearings, the balls of the bearings are imported separately, because I made the assumption that they have a rotational speed of half of the gear. You should see the definition of the oil level, as Mr. Habecker also has shown. For the simulation, I used a particle size of 1 millimeter, a current number of 0.2. The speed of sound I used according to the highest circumferential speed of the gears, which is obviously in this case quite the same for both gears, almost the same. The turbulence model was switched on. For the slip factor, I used a value of 10 between the gears, and otherwise, so between gears, between oil and housing, I used a slip factor of 1. With this slip factor, I saw better results, and it was for me I could simulate the squeezing losses more accurate. The pressure smoothing was switched off. The surface tension model potential, and as I said, a constant oil temperature of 40 degrees, like in the test. So also in the simulation, so a constant oil viscosity. So, and here you can see a comparison between the simulation and the test for an exemplary operating point. without active lubrication. I just start this animation. So it's all 5 seconds seconds in real time simulated. And yeah, the corresponding picture from the videos that we did at the test, you can see on the right. Yeah, and it can be observed that yeah, we have quite similar behavior in simulation and test. So yeah, the areas where we see oil on the right, also in the areas where we see oil on the right, we also see oil in the simulation. Also nice to see is that the remaining oil in the sump is also quite equal between both, but in the next example it will be even more obvious. Yeah, and here at the bearing, at the upper bearing, you see that there is not so much oil in both cases. So this is without the active lubrication. And now I'll show you one example with active lubrication. So it's same speed, same oil. Then I start this animation. Yeah, and yeah, also here you see a good, yeah, it's quite similar results. You can, what is really nice is that you see here at the bottom, so we have the oil pump activated, and so, but we have not changed the oil level. So, of course, due to the oil which fills up the oil guide, the oil level will be reduced, and you see that we have almost the same oil level in both in simulation and test. Yeah, so in this case, it was almost critical that the sump runs dry and the pump would suck air. So yeah, these effects can also be simulated very well. And you see here, in difference to the other example without active lubrication, we have much more oil here at the bearing at the top. You see the oil coming here from these orifices. You can restart it once again, maybe. So you see the oil coming out here. And also in the test, we could see that there is more oil. Even though it does not look so maybe compared to the other picture, but here without active lubrication, we only have some oil mist around the bearing. But here with active lubrication, yeah, we have really an oil film in this region. So here you see this from the test, the video from the test to show you the dynamic of this. I know it works. Yeah. So you can see some seconds of this test. So even in the stationary state, there's yeah, happening much. So there's always movement. So it's not a constant oil flow. It's always yeah, some action inside this transmission. And this is only for 1000 RPM. Yeah, for the higher speeds, of course, yeah, it's then you see almost every oil everywhere. But yeah, still nice to see. Yeah. So and then we have, of course, other losses in the transmission, which are relevant for the drag torque. So these are the bearing losses and the sealing losses. And there I use formula-based calculations, which I included in my MATLAB Simulink model. For the bearing losses, I used the calculation approach by SKF. So it considers 4 components of the losses: rolling frictional moment, sliding frictional moment, the frictional moment of seals, and yeah, frictional moment of drag losses, churning and splashing. And for the sealing losses, I used an approach yeah, which was formulated by Linker. You see the source of this this book actually at the bottom. So the losses in this approach are according to depend on the shaft diameter, on the viscosity class on the oil temperature and on the rotational speed of the shaft. So now I will come to the simulation results and the comparison to the measurements. First of all, we have three different oils. And first of all, I begin with the low viscosity oil that we used, which is an automatic transmission fluid, so an ATF. You see the simulated and measured drag torques for the three different input speeds. So we had did the test with 1000, 3000, and 5000 RPM input speed. You see the dot, the solid line is for the simulated values, and the dashed line is for the measured values, and then for the three different oil levels. We can see a very good correspondence between simulation and test. Only here at 5000 RPM with this oil we have a larger deviation, so we overestimate the losses in the simulation. But this is due to numerical settings. In this case, a smaller slip factor would reduce the deviation. But for this investigations, I kept this as a constant value. So that is could be improved in this case with the experience that you gain, for example, in a test. So you can see here the relative deviations of simulated to measured drag torques. So on the horizontal axis, we have the speed and the oil level, and on the vertical axis, the deviation. And you see that we are in many areas, or most of the areas, we are below 20% deviation. And in the remaining areas, still between 20 and 40%. So on this slide, you see, as an example, how the losses distribute. So the single losses, we have for this ATF oil, we have here the values for the low oil level and 1000 RPM. The left bar is always for the tests and right for the simulation. You see, quite good result. And the biggest part of this losses actually come from the sealing losses, at least according to the simulation. So when we go to a higher speed and keep the oil level at the low oil level, we see the sealing losses here in green. They are not, they do not change. So what changes is mainly the hydraulic losses, and the bearing losses actually reduce quite a little bit. And the third example, where we also have a very good simulation result compared to the test. So we increase the oil level to the medium oil level. So the hydraulic losses really increase very much. Also the sealing losses, they are not influenced by the oil level, and bearing losses also increase due to splashing losses. So then we have the medium viscosity that has been investigated. This was a 75 RWTH transmission oil. The same representation as before. Here it's a bit different. Here we underestimate the simulated, the measured losses in our simulation for this operating point at 5000 RPM and the high oil level. But this can be explained by the oil aeration, which was also noticeable in the test. This leads to an increased viscosity, but was not investigated the oil aeration was not considered in this simulation. So also here we have in many operating points deviations between 0 and 20, respectively -20%. I see this deviation here at the 5,000 RPM and high oil level, which I just explained, and some deviation coming to a low oil level and low speed, which could be explained by the sealing losses, which are maybe simulated or calculated too high. And the third example, the high viscosity oil is 140 W80 transmission oil, where we can also see a good match between simulation and test. So interestingly, with increasing viscosity, the drag torques reduce in, for this transmission. And but you see here again, it is the case that we underestimate the losses in the compared to the test, but here we have quite small deviation. So here the same, so the relative deviations, where you can see, especially at the low RPM, the deviations which go up to 60%, but this can be most probably explained by the losses of the ceilings. So now I come to the summary and to the conclusions. So in general, we have a very good match between simulation and test, even with the same numerical settings for simulation with different oils. So as I mentioned, I kept this slip factor constant. So when you have experience with a certain transmission and a certain oil, you can of course optimize this, and then for similar applications, you already have more experience, and then you can adapt the slip factor. But I wanted to keep it constant because I did not have the experience in advance, and even with that, we have very good results. So as I mentioned, less than 20% deviation in many cases. We can observe a very similar flow behavior in simulation and test. And the 3D CFD with Particleworks delivers more accurate results of the hydraulic drag torques compared to formula-based approaches, which I also use in my MATLAB Simulink model. But these formula-based approaches are of course not so flexible. And a big advantage is that 3D CFD enables the visualization of the oil flow and therefore an assessment of the quality of lubrication, which obviously is not possible with formula-based calculations. So thank you for your attention. And do you have questions?
I actually believe there's quite a lot of questions. Yes, in fact. Let me just share my screen again. All right. Thank you everyone for your attention, and thank you Mr. Mole and Simon obviously for your presentations. We have now reached the end of the session, and I did notice that you did send us quite a lot of questions during the webinar. Thank you very much for all of those. We would like to take a few minutes just to answer as many questions as we can. So I have already, Mr. Mole and Simon, I've sent you a few questions, so I really want to leave it up to you if you want to pick the question that you would like to answer, or if I pick something. I mean, one question, for example, that I see is, could the oil aeration be considered in the simulation? Perhaps you'd like to answer that one.
Yes. yeah, that it would be possible to consider the oileration, so the influence of air inside the transmission. That's definitely possible with Particleworks, but yeah, I did not consider this for the simulation. Huh?
Okay, thank you. One of the other questions I see is what are possible sources for deviations between simulation and test results? Which one of you would like to answer that one?
Yeah, I can start.
Okay.
So yeah, so deviations, of course, are the other losses, possible deviation, other losses which have to be considered, as I mentioned. So bearing losses and the losses of the ceilings, and yeah, other sources could be, of course, a particle size, which should not be too large, and yeah, and of course. Yeah, I think the squeezing losses and the slip factor. So as I mentioned, I increased the slip factor in order to have to get the squeezing losses correctly, because yeah, I did not change the geometry of the gears. So I have in this case the drive flanks in contact. So a very small backlash of the gears as it is in reality, and but of course, yeah, the particles do not really fit into this gap, and so I would not be able to simulate the losses correctly, and by increasing the slip factor, I made the experience that I get better results. Huh? Mm.
Okay, I see. Thank you very much. Let's look at, I don't know, maybe one or two more questions, especially with look at the time. I've got one more on the particle size. It says, has the influence of the particle size on the simulation results has it been investigated?
Yeah, I've investigated it. Yeah, first I started with larger particle size of 1.5 millimeters, but then after some time I came to the conclusion, also in discussion with Mr. Habeke, that I have to go to 1 millimeter, and this led to really to an improvement of the simulation results. So with the 1 millimeter, I found a good compromise. Of course, smaller, yeah, might be better, but yeah, I also had to look at the simulation times, which are still quite fast. But I also had many operating points to simulate, so this was a good compromise.
Mm-hmm. Okay, thank you very
Yes,
much.
if I may add.
Yeah.
Yes, of course, in general, a finer spatial discretization, so smaller particle size would, of course, enable a more accurate solution. But as Mr. Moll said, I think he had quite a few simulations to be run, so there's always a compromise to find between reachable accuracy and available calculation resources.
Mm-hmm. Thank you very much for adding that information. At this point, just looking at the time, I mean, we've had so many questions. I apologize, but we're not going to be able to cover all of them. Unless you two, Simon and Mr. Habeck, if there's anything else you'd like to answer, then please interrupt me. If
we just check.
Yeah. Because otherwise I would conclude the webinar for today. But I'm going to give you a moment. But
yes,
either way,
in general, we'll be happy to answer the question afterwards as well via email.
Yeah, I think
yeah, that's what I was just gonna say. I mean, even if we don't get to answer all of your questions right now, we apologize, but there's just been so many. But feel free to send us an email. I'm gonna show you my email address in a moment, and then we can provide you with further information. All right, then I would say this concludes our session for today. Thank you, Mr. Moll. Thank you, Simon, for answering these questions. One more thing I would just like to introduce to everyone is our Particleworks Technology Days before we finish. Our Technology Days are free of charge, one-day events where we offer you a hands-on approach to get to know the CFD software and its multiple application possibilities. We at Engines of Germany, we have a tech day coming up on June 8th, and our UK colleagues have one scheduled for June 10th. So there's still some room available for participants in both events. So if that is something you would be interested in, then feel free to shoot me an email at a.dubeler@enginesoft.com. My email address you can see right there. And I will be happy to provide you with further information, or also, as I just said, if there's any more questions, anything else you'd like to know, please send me an email and we'll be happy to provide you with all the information you need. This being said, I would like now to thank all of you for your attention and for your interest in the matter. Also, thank you, Mr. Moll, thank you, Simon, for the time and effort you have invested to make this webinar possible. I guess that's pretty much all I have to say at this point. Thank you, everyone. Thank you for being here. Goodbye and have a great day.
Thank you. Goodbye.